Welcome to this Trimble Business Center video tutorial about processing tutorial data from our TBC tutorial page. And we have already here run some processes on the tutorial data, DGI, aerial survey data. In the previous video, you can see where to download it and how the data is structured. We did process the baseline successfully, and we want now to go into the adjust photo stations and to run the adjustment, which will then now make a relative adjustment and absolute adjustment. So we will hit the adjust button and then fast forward to the successful process. So have fun, and we'll see it in a moment. So the relative and absolute adjustment was successful. So we will now apply the adjustment. So we will now write the new orientations for the XYZ position and the orientations omega phi kappa for our different photos. And we want to take a look at the report. There are many different ways how you can check the absolute adjustment, and this is really also for complex data not so easy. To help you to simplify this whole process, the PDF was generated, and also what we are offering is the workflow bulletin. So you can go in TBC to the support page, go to the release notes, and when you open the release notes, then there is also here, additionally to the release notes, bulletin. And one of the bulletins, or here it's a workflow bulletin, is error photogrammetry for surveyors. And when you check it up and open it up, then you get following PDF, which goes into detail about the workflow for it. So what we want to use it here in our video is the part where we talk about the absolute adjustment and the adjustment report. And so let's here just use this here to check our result, also based on the workflow bulletin. So the first page is general information about the project. We will then see in this one here our scale of the world and also our average height above the terrain. So when we take a look here, then we can see this is here our scale and our average terrain height. On the next page, we will see now here what images are adjusted. And this is very important. We don't want to see any red circles because, as he mentioned in the yellow box, this would indicate a problem in our adjustment. So we want all our images, if they make sense, to be adjusted. So in our case here, all our photos have been adjusted. We can also see there's here in this part mentioned how many photos have been eliminated from the adjustment, and typically if all images are nicely shot and they have a correct content, they should be able to be adjusted. The next page of the document is the type point distribution. This is an important part of adjustment. Always we call it connectivity. And we will see there's also another graphic which will help us to see if there are some single images with not so good connectivity. It's also, we can call it block stability, which is somehow going with each other, these two terms. And because the images are overlapping very strong in UAVs typically, and when you have an 80-80 overlap, for example, then we tend also to have points that are more than 16 times connected. This would be nice. So we have then this graphic showing us here in general for the whole block how good they are connected. And we have here this legend In our case, our legend here is now going from 0 to 11, 12 to 22, and we have even images that are more than 33 times connected. So this is typically here not 8080 flight, this is an 8585 flight. So we have a lot of connection between here, these different images. And we still see that we have here areas with red. And when we know our content of our images, we know these are the trees. There is here thick trees. There is here an open space. We can see here these green and blue ones, and then it goes here back. And therefore, this orange part, which is still more than 12 times connected, is well established. This is our road. And here are tree parts on this part, and yeah, they are difficult to match in this case. Still, this could be still an 11 time connected point. Mainly we just categorize it in 4 parts and try to here equally spread this here through the block. If we are interested into more about it, then we could here take a closer look in either EOS Master, where we can send this here and take a deeper analysis, or also in the temp folder. Both of these parts will not be covered here in this training. On the next page, we have the same thing, but now statistically shown with a table. So listing the whole part. So in our case, this would then be here. And then we can see here that only 16% of our images are up to 3 times connected, and most part of our images is more than 3 times connected. And here we see the distribution of our points. The next slide is now about our measurement instrument. So the camera that we have in our drone photogrammetry is like our measurement instrument, and this camera needs to be calibrated because we want to get the highest precision out of it, and therefore because we have high precision GNSS, and we can here calculate now for the camera new values for focal length, for the distortion, and this is exactly what is now shown in the next graphs. So in our case here, we can now see here that we have a new focal length and also new distortion values. When we take a look at the distortion, then we need also to have a principal point, because the distortions are in a systematic way defined, and they need an origin, and around this origin our distortions are defined. And what we want to have is here equally growing curves going either up or down in this case here for our project. Then these are now here our polynomial, this is now here our radial systematic components in this case here. And then we also here have these coefficient distortion table, where we just put a grid on top of our image here, 7 by 5 lines, and just to see how the distortions here are distributed over our sensor. So this is now our distortion in the camera original. We see here we can have up to 42 micrometers of distortion, and therefore we want to eliminate them by defining distortion corrections. And after we apply the distortion corrections, then these are our remaining distortions. So there are an average around 1/4 of a pixel, and they are irregular distributed, which is good. So we don't want to have here still some systematics. You see in the original one there are some systematics, and also the values here of course are much bigger, so don't be misled by the length. This one length here is 42 micrometers representing, and this length here, which is perhaps one of the largest one, is representing only 1.2 pixels. So this is how we were able now, after we have all the tie points connected, which are multiple matched, and help us therefore to define the uncertainty in some areas, how accurate we can measure now in our measurement instrument. which is the camera. And this is good because we want here to measure very accurate in our drone. The next part is now here about some legends of the histograms that are coming now. If you want, you can take it here in more detail, just that you are aware. So the threshold for the first histogram is at 50 points for one photo. So that means if in our first histogram, which is this one here, if there would be here an image below this red line, then this one image would have less than 50 type points or measurements in it. And this is also now what we talked about, the connectivity. Before, the connectivity was in the whole block with how many multiple matches we have, but still we want every single image also to have enough type points. We want to have them more than 50, and we see here this is by far exceeded. We have here starting at 280 measurements for the first image that we have here. So therefore, this is there is no image below this part. Then secondly here the distribution. So here this is now this is the classic way of the Gruber positions, but still we want that every image has in all, if I would divide a photo in 9 equal tiles, then we would have an upper left, an upper right corner, then a lower right, lower left corner, and then the fields in between in the center. So 9 equal fields, and we want in all of these 9 fields to have type points. Just to check, is there any image here? And we see all images have in all 9 areas type points. So the distribution of the type point for each one everywhere is well distributed. So just from a statistical point of view, we have in all images everywhere in the type point areas, in these Gruber areas, we have here type points. And the last histogram is now just here using the 3 times sigma for our check if there is here images going here in a bad direction. So this would be here around 3.18 pixel. And if we would have one photo that exceeds this 3 times sigma value, then this would then be again an indication. Perhaps this image is blurred, or the image is under or overexposed, so something went wrong, that this one image here has a lower root mean square for all its type points. So again, simplification, we try here with the 3 histograms to show if there are some single images in a connection way, and also in the accuracies or the uncertainties of our type points somewhere showing up, and it doesn't look like in our case. And here just one more time in this workflow bulletin, just here again summarized. So we don't want to have any of our images below this red line, and also we want them to be here also below this 3 sigma value here listed in our histogram. Of course, besides all the connectivity or block stability, and also about the statistics, about here the connectivity from the points, we also have the accuracy values. And this is of course something where we want to reach a specific accuracy, and therefore we have here the block adjustment results, and they are divided into different components. So the first one here is the typical sigma naught value that we have. So here we want to reach, depending on what pyramid level the extraction was done, to reach our pixel accuracy. Then we have our standard deviations of translation, and so this is already here nicely written. So how accurate are the photo positions adjusted in the air? So how well did we establish the positions? In our case, everything is bound to the GNSS, so this value should be nice because everything is referenced to the GNSS. We did not measure control points, so we will see how good are our terrain points on the ground. So here, how accurate are the type points positioned And typically with the ground control points here, this can then also here be more tightened to it. But we have such good overlap, I think also this value should be fine, just purely based on our GNSS. Then we also have the GNSS itself. So these are now the RMS values here. So how well are they determined? What uncertainties do we have in it? And then the rotations here for drones, typically they will not reach 2 or 3 millidegrees. So they should, depending how strong the wind is and all these parts, differ. So let's take a look now at our data itself. So these are our input values that we have. We have high precision GNSS, so we started with 2 centimeter. And when we now go to the result, then we see now, of course, everything is bound to our GNSS. The standard deviations are centimeter accurate. And on the ground, we are reaching here still 2 centimeter in position and 5 in height. If we would now add the control points that exist here for this project, then this value would probably still stick in the same area, but of course with the control points we have a better stability and a good reference to our real data that we want to combine it. So therefore this is something to be aware. And we see also of course the standard deviations here are nailed down, but we see in the RMS that our GNSS is something around 3 centimeter accurate. So if we would add the GNSS, then these values will probably move a little bit up, go towards 2 centimeter, because they are in this uncertainty level. And finally, I mean, very much known for adjustments are these statistical error ellipses. So we want to have these error ellipses of equal size. So we want them to not be completely different in size in the center and the outside part. Typically they tend to the outer border to become a little bit larger. This is common, but if I would have in the center a larger one than outside, this would then be again a warning or something I have to be suspicious about. Also, in general, we want them to be more round and not elliptic. We want not to have here a strong XY difference in our GNSS. We want to have them be in similar quality. And also what we want is, as it's also shown here, to see what are our real values. Sometimes they can be large or small on the screen, just to be aware of the scale that is here defined in the legend. So, and we take a look here on our data here. We want them to be of equal size. And then in general here, we have here an average of 1.4 centimeter in position, and the max is 2 centimeter. So this is really exactly what we expect. Also, when we would know the terrain is here falling down, so this here is closer than this part here. So that means the pixel sizes here are a little bit smaller than here. So it's not flown completely with the same distance to the ground, mainly because our main interest of this project is here on the upper part, on this left side, which is upper, and therefore the error ellipses here become a little bit smaller because the tie points measured also here have a longer distance to travel, and therefore here they will be of lesser quality. And also here is more trees and forest part. So exactly what we expect them to be here, more uncertain than over here. Therefore, as I say, statistics should never surprise you. They should just help you to understand and say exactly that's what I expected for it. Then the next slide is GNSS residuals. And again, here we want to see if there are still some systematics in our data. So when we take a look here, well, this is now here about the omega phi kappa or orientations. But let's go here. Then we want not all the vectors show in one direction. So if everything would point to the right side or everything to the up, then there could also be some systematics in it. And Still, this can be fixed when we would measure then control points. They would help us then here also to solve here shift and drift corrections in our GNSS, but just for us here to check. And also again, don't forget, always look in the scaling. So we are talking here about residuals in the size of about 4 centimeter here, and in the max of 14 in the outer part. So that's about now our report for just purely running it on the GNSS data. And we will then in the next video show also how to measure control points. And then after measuring the control points, we will then again adjust the block. And therefore this information here, so the GNSS with the 2 centimeters, will also be applied then in the next video, but also our ground control points and the measurements of the ground control points will have an influence, and this will also then cause a new camera calibration, but they should be very similar because we already have here a high GNSS precision, and therefore this will then come to a close or similar result. In the workflow bulletin, this is already here described, but this will not be part of this video here. Also here we are talking a little bit about how to distribute your control points in the right way. So this is also something we will talk about it. And that's about for the workflow bulletin concerning the adjustment report. Our project is now ready to continue with creating deliverables also. So we don't need to measure the ground control points. It's totally sufficient just to run your drones based on high precision GNSS. We still would recommend it to at least measure 1 ground control point, because with 1 additional ground control point, this gives you a much better block configuration for the camera calibration, also to make your data fit to your project reference, whatever it is, because typically your ground control point is part of a survey part, and therefore they will also help you to make it fit to the real world. Thank you first very much for watching this video up to here. So the next part will then be adjust photo stations with GCPs, if you want to follow with the next one, or if you think the adjustment is fine up to here, then you can directly go to create deliverables with this result. This is both acceptable and fine, just that you are aware. So thank you for watching and have a nice day. Goodbye.